Hello guys, welcome back. So last part of cycloalkanes is left. So it says the kinds of rings in cycloalkanes and their stability, right? So there are a lot of cycloalkanes in different sizes available. Cyclopropane, cyclobutane, cyclopentane, cyclohexane, and then cycloheptane, cyclooctane, cyclonone, cyclodecane. But most commonly, if you see in nature, no, you can see glucose like glucose, fructose. Most of them it will be 6-membered ring, and then you will also find 5-membered rings. But very rarely you will see 4-membered ring. Some amount you will see 3-membered ring, and very rarely 7-8-membered ring. Okay, so it's mostly the nature consists of 6-membered ring. So this is 3-membered ring is highly unstable. This is also very unstable. 5-membered ring is quite stable. Most stable is 6-membered ring. But 3-membered ring is kinetically favored. That means formation happens very fast. Because you understand, size is small. Attack can happen very fast and then reaction can happen. So thermodynamically means as a product, very unstable product. But formation happens very fast because it is kinetically favored. Okay, kinetic means you understand how fast it is. You look at the intermediates. This one is unstable both thermodynamic and kinetically, whereas 5-membered ring, if you see, it is both kinetically favored and thermodynamically favored, and interestingly it is actually more kinetically favored than 6-membered ring, right? Because it is shorter, attack is faster, so it is kinetically more favorable, but thermodynamically 6-membered ring is more favorable. This is very important point what I told just now, comes in lot of competitive examinations. Please remember this. Okay, now we'll talk about how do we determine how stable is the cycloalkane. We determine by looking at the strains. So these are the two strains which makes them unstable. First strain is bare angular strain. As the name itself indicates, angular strain. So we know all the carbons in the cyclohexane are sp3 hybridized. So the angle should be 109 degrees. If anything is close to 109 degrees, it is stable. However far it is from 109 degrees, more or less that much instability it gets because of this bare angular strain. The second one is torsional strain. Now if eclipsing hydrogens are there and then steric hydrogens, they start repelling each other, and that gives another strain called as torsional strain. These are the two strains which gives them instability. Let us look at it. Cyclopropane. Now cyclopropane, you understand, it's a very small 3-membered ring. You cannot push pull. It cannot have any other conformation like cyclohexane. We talked, it has chair conformation. This cannot have. This is the only structure possible for cyclopropane. The only structure possible for cyclopropane is planar structure. Now it has hell lot of instability. First thing you see this angle. This is 60 degrees. How much is the tetrahedral? All of them are tetrahedral. So the angle is 109 degrees, 28 minutes expected, but it is only 60 degrees. So almost 50 degrees of strain, highly unstable. Apart from that, you see this H and this H and this H. 3 hydrogens eclipsing each other. Similarly, this H and this H, they are eclipsing each other. Creates huge amount of torsional strain. Okay, so thermodynamically highly unstable. Okay, but kinetically it's quite favorable because very close. Imagine I have to form something like oxyrane ring. So I'm talking more from not from cyclopropane point of view. I'm talking from the size of the ring. 3-membered size ring is quite kinetically favored, especially when you do synthetic organic chemistry. You have to know this. You can easily form 3-membered ring, though it will not be very stable, but it forms very fast. So something like this, if you are forming, you have something like OH was there, you put some base, it becomes O minus Na plus, and then you attack with this bromine, very fast it happens. So therefore it is kinetically favored. Now let's talk about cyclobutane. So cyclobutane is 4-membered ring. So if it was planar, the angle is 90 degrees. So 90, 100, 110, 109. So it is close to 20 degrees angular strain, not stable. And then again all this was there. All hydrogens are eclipsing each other. So it creates both torsional strain and bare angular strain. So cyclobutane never exists in planar structure. It changes the conformation. It becomes kind of envelope. It's called as envelope conformation. Now also angle, it doesn't reach 109 degrees but close to 109 degrees, okay. And still some hydrogen, like you can see this hydrogen and this hydrogen, they are eclipsing each other. This hydrogen eclipsing each other. So though it reduces quite a lot of angular and torsional strain by going in an envelope conformation, but still it is not stable, neither kinetically nor thermodynamically, okay. The attack is not very favorable, it's not quite close by. Now 5-membered ring, if it is planar structure, the angle you can see is 108.5 degrees. I am not very sure about the angle, but it's more than 108 degrees and less than 109 degrees. So you know, angle expect is 109, so it's very close to 109, so it doesn't have angular strain. But if it is in planar, see this hydrogen, this hydrogen, this hydrogen, this hydrogen, this hydrogen, they are all eclipsing each other. And this hydrogen, this hydrogen, this hydrogen, all these hydrogens are eclipsing each other. So they have huge amount of torsional strain. So this also undergo conformation. It comes out of plane, and you know, it is basically one of the hydrogen, one of the carbon pulled out, and then so this whole thing has changed, and then you get this conformation, okay. So now this 5-membered ring is kinetically more favored than cyclohexane, but thermodynamically little less favored. And then we come to cyclohexane. Cyclohexane, if it is in planar conformation, angle becomes 120 degrees. Now all this sp3 hybridized, angle expected is 109 degrees. So 10 degrees, 11 degrees strain and lot of torsional strain you can see. So it never exists in planar structure, just not possible. So it goes mostly from one chair to another chair, and we have talked about other conformation also it goes through, but basically it goes from chair to chair conformation. Here it is having zero strain, either torsional or angular strain, both strains are not there, and so it is thermodynamically very favored. And then as the ring size increases, as I said previously, it becomes both kinetically and thermodynamically less favored, and it occupies different conformations but still doesn't gain that kind of stability, right. Next we'll go to next topic completely, that is unit 3, okay. So unit 3, we are going to talk about elimination reactions, carbon-carbon sigma bond, carbon-carbon pi bond. I'm starting with the carbon-carbon sigma bond. So first is formation of alkanes. So formation of alkanes, generally, you know, alkanes nobody forms. It's available abundantly in the in nature. All this petrol, you know, mostly it is hexane, then little bit of heptane. Some amount of octane also might be there, heptane will be there, but mostly it's hexane. So all these are found in nature. You understand this? There are two things. One is photosynthesis, one is respiration. In respiration, you break the less oxidized molecule into the most oxidized form. It breaks up into carbon dioxide. So carbon dioxide is the most oxidized form of carbon. So initially, even if you eat cellulose, no, cellulose will break into glycogen, then breaks into glucose, and then finally it goes to carbon dioxide. So respiration is always oxidation, and photosynthesis is always reduction. So it takes carbon dioxide, that's the most oxidized form of the carbon. It first reduces to glucose, then reduces to sucrose, then more it goes to cellulose kind of thing, starch. All these are much more reduced form. So photosynthesis, so whenever reduction is there, there is storage of energy. You know, glucose stores much more energy. Then more than glucose, starch will store energy, and more than starch, cellulose will store energy. So whenever reduction happens, there is storage of energy, and as soon as oxidize, when glycogen becomes glucose, it releases energy. When glucose becomes carbon dioxide, it further releases energy. So whenever oxidation is happening, energy releases. So, but in lab we do prepare, some ways are there. One is you take alkyl halide and you react it with sodium in presence of diether. So this is diethyl ether, Et2O. Ether, you know, formula ROR prime. So ethyl C2H5O, C2H5 is there. You react with it and you get RR linkage. This is one way of forming. You can take two molecules, so Rx and R prime X, then you will get RR also, you will get R prime also, and you get RR prime also, okay. So not a very selective reaction, not a very good reaction. X, generally they use bromide, so they will take generally alkyl bromide. So what you get is NaBr. Then there is Wood's fatigue reaction. So Wood's fatigue reaction, you take aryl halide and alkyl halide react with sodium, same thing, then you get alkyl aryl linkage. Here it is alkyl group, it is something like CH3 or C2H5, C3H7, anything. And here where in Wood's fatigue reaction you are using aryl plus alkyl. Okay, spelling you see WURTZ. Okay, next is reactions. Okay, so these alkanes nobody reacts, very tough to react them because they are highly stable. You know, carbon hydrogen bond breaks, but unless some activating group is there, very tough to break them. Carbon bond almost they don't break unless you use extraordinary extreme conditions. So but if you use bromine, what happens? First bromination, one bromination happens, then second bromination happens, then it will happen here, then it will happen here. You get millions of products. Okay, like every hydrogen will be replaced by bromine with time. So it's very difficult, synthetically not useful, but you can control to a certain extent, especially with if you take some good molecules, something like if you take tertiary butane. Now this hydrogen, if you react with bromine and you don't allow it to, you don't put in the reaction vessel and leave it under sun. H nu is light, okay, photolight. So generally you don't you can put photolight, UV light in lab also, but generally just put in sun. So you don't leave the reaction in sun and leave forever. If you leave in sun forever, all the hydrogens will be replaced by bromine. Okay, but if you like put in 10 minutes and keep checking, you'll see that first hydrogens to go will be this tertiary hydrogen and you get bromine. Why? Because this reaction goes through free radical mechanism. Okay, so I was saying you get this major product if you immediately stop it after 5-10 minutes or you keep monitoring reaction. Most of things you'll get this. Other than that, after first bromination will happen this carbon and then start here, you'll get a lot of product. But you can have certain amount of selectivity. What's the mechanism? Mechanism free radical. First bromine reacts with the light, UV light generally, or visible light also works, and it breaks up and you get Br dot. And then this it breaks up this hydrogen you get here. Now this is a tertiary radical. Now tertiary radical you study, tertiary radical is more stable than secondary than primary because radicals are electron deficient species. If hydrogen would have been taken here, you would have got CH2 dot. So that is primary because two hydrogens are there. Primary radicals are not very stable. Tertiary radicals are much more stable, and therefore reaction happens here and not here. So first reaction you get is this, then it stops. Okay, thank you.